Okay, welcome everyone to lecture 6. In lecture 5, we had finished the analysis for the indirect and the direct MRAC cases. In this lecture, we will talk about the case where the plant is not entirely linear, which is the case for real systems where you may have some nonlinear terms in your system dynamics. So, let us assume that the plant in this case is given as A x plus B u plus delta x. So, instead of the LTI plant A x plus B u, here we have a nonlinear term delta of x. So, it's a nonlinear function, uncertain. So, delta of x is not known. So, how do we design the controller u in this case? So, typically when we have some uncertain terms, uncertain nonlinear terms in the system dynamics, we try to cancel those nonlinearities using the control input. In many cases, the nonlinear terms may in fact be helpful for the stability, but then we need to exactly know what those nonlinear terms are. In case those terms are uncertain, we are not sure whether those are in fact going to be useful for the stability, and it is in fact better to somehow account for these terms using a robust controller. Certain nonlinear terms can also be dealt with in a different way using adaptive control, as we will see in this lecture. So, we assume that these nonlinear term delta of x is in fact we a structured uncertainty. So, there are two types of uncertainties. One is a structured uncertainty and the other is an unstructured uncertainty. Structured uncertainty is one where although the entire term is not known, but we know the structure of the uncertain term. Unstructured uncertainty is where we do not know the structure of the uncertain term. So, here we assume that this delta of x is a structured uncertainty, and in this case it is also a matched uncertainty. So, why it is matched is because delta of x occurs in the same channel as the controller. So, using our control input u, we can directly account for the effect of the of this nonlinear term delta of x. If say we had some term like plus c times delta of x, then we could say that that term is an unmatched uncertainty that would be more difficult to deal with the control input u. In this case, we assume that the uncertainty is a matched structured nonlinear uncertainty. So, again in this case I consider a scalar case. So, let us reduce these matrices to scalar terms. It just makes the analysis much easier, and then you can later work on the vector case. Okay, so as I mentioned, we assume that delta of x has a structure, and it also has a very special structure which is called as linear parameterization. So, delta of x is given as theta transpose phi of x. So, it is a linear combination of basis functions. These basis functions phi of x are known, the weights that these basis functions are combined are unknown and given by theta. So, theta is a vector of unknown parameters. Theta is defined as theta 1, theta 2 till theta n, and phi of x denotes the basis function, and it is a vector of known basis functions. So, phi 1 of x phi 2 of x. So, notice that theta transpose phi of x is still a scalar. Okay, so, the objective is again to follow the reference model. So, we want you to be a model reference adaptive controller which follows the reference model given by AM XM plus BMR, and again we say that AM is less than 0, R is bounded, which means that XM is also bounded. Okay. So, I should write that this uncertainty is linearly parameterizable. And that is why it can be handled using an adaptive controller. Otherwise, we would have to use some other kind of controller. So, we will see how these the fact that this uncertainty is linearly parameterizable helps us in our adaptive control design. Okay. So, the again we the mechanics remain the same, and by now I hope that you are familiar with the mechanics. We start with the tracking error, which is the difference between the plant state and the model state, and then we construct the open loop error system given by E dot. So, in this case we get the B delta term because of this nonlinear term which we did not get before, but in this case we do consider this term. Okay, so, so the controller, how do we so the challenge here is how to design the controller U to stabilize the system. So, if the delta term wasn't there, we would go ahead and design the direct MRAC or the indirect MRAC case. Because there is a delta term, we would have to modify this controller, maybe add an extra term to account for this nonlinearity. So, the control input intuitively would be a combination of two terms. One would be a nominal controller and the other one would be a term which is used to account for this nonlinear term delta. So, U would be a combination of the nominal MRAC. So, U would be say k x hat plus k r at r plus a u delta term. So let us call this as a nominal term, and this is the term u delta is the term which is used to account for this term b delta. So let us just substitute for the delta. So E dot is given by A x. Let us not substitute for u right now. Okay. Now, since theta is unknown, we can choose u to be a certainty equivalence controller. Certainty equivalence controller is one where you write the controller first as if there is no uncertainty, and then whatever terms are uncertain, you just consider their estimates. So, in this case, suppose k x and k r were known, we would choose the control input to be k x x plus k r r, plus for this case we would choose theta transpose phi minus theta transpose phi, and cancel and try and cancel this nonlinear term. But since we do not know this theta, we choose an estimate. So, u is given by k x hat x plus k r at r, and let us just say that this is minus theta hat transpose phi. Okay, so this is the nominal controller, and this is the part which is used to account for the nonlinear term. Okay. So, we need to design the update laws for k x hat, k r hat, and theta hat. The fact that this term is linearly parameterizable helps us write it simply as a linear combination of the functions x, r, and phi. Okay. So, again we for the nominal case, it's a simple case of MRAC. So, we consider that there exists ideal k x and k r such that a plus b k x is a m and b k r is equal to b m. So, these are the matching conditions, and they are trivially satisfied for the scalar case. For the vector case, they may not be satisfied. So, you have to be careful when dealing with the vector case. So, they may not exist enough structural flexibility in the plant to satisfy these matching conditions in the vector case. Okay. So, the certainty equivalence controller is given by this combination of two terms. When we substitute that in the error system, we get the closed loop error system. Which is given by so here, like before, k x tilde is the parameter estimation error for k x, and it is defined as k x minus k x hat. K r tilde is defined as k r minus k r hat, and theta tilde is the parameter estimation error for the parameter theta. So, it is given by theta minus theta hat. So, these hats are time varying, kx, kr and theta are constants. Okay. So, this is the closed loop error system, which will be useful for us in when we do the Lyapunov analysis. Okay, so let's go ahead and choose a Lyapunov function candidate, which is always the next step. So, let's choose a Lyapunov function candidate. So, V in this case is a function of E, kx tilde, kr tilde, theta tilde, and it may also be a function of time, but in what we choose is in fact a time invariant function. So, as I said, there can be other choices of Lyapunov function from what I show here. This is just one way to choose Lyapunov function candidate, but they may exist many other ways to choose Lyapunov function. You can try some other options and see if they work out. Okay. So, if you remember, for the case where both A and B are unknown, so this is a scalar case that we consider for both the direct MRAC, we found that a good Lyapunov function would involve the absolute value of the parameter b. So, this is a positive number divided by 2 gamma x. So, it is very similar to the Lyapunov function candidate that we chose for the direct case. Without the nonlinearity. Now, since we have a nonlinear term here, which is linearly parameterizable with the unknown parameter theta, we need to include that as well in the Lyapunov expression, and since theta is a vector, so the way to include that would be through this expression. Okay, so here we consider that this gamma theta is the adaptation gain and it's positive definite. So, this is very similar to the gamma x and gamma r that we have chosen, which are in the denominator. So, here we have gamma theta inverse. Okay. Okay, so the next step is so this is the Lyapunov function candidate that we have chosen. Let us look at the time derivative of v. So, v dot is given by e dot plus kx tilde and minus kx dot plus b over gamma r kr tilde minus kr hat dot plus 2. So, 2 will disappear, tilde transpose gamma theta inverse and theta hat dot, right. Okay, so let us substitute for the closed loop error system from above. So, we get AME. Oh, so I think there is a sign mistake here. So, here we will get a positive term. Minus b kx tilde x minus b kr tilde r plus b theta tilde transpose phi of x. Okay, and then we have minus derivative b over gamma r kr tilde kr hat dot minus right. So now we have set up the problem for designing the update laws for kx hat, kr hat and theta hat. Okay, so we want to generate the update laws for kx hat dot kr dot and theta hat dot. Okay, so for kx hat and kr hat we can simply use what we had obtained earlier, and that is in fact going to cancel these two terms. So those would be minus gamma x e sine of b. Okay, so if you choose it, then this term will cancel with this term, and let's choose kr hat, be minus gamma r e sine of b. Then this term will cancel with this term. Okay, and so for this case we have to choose the update law as gamma theta phi of x. So we want to cancel this term, so the update law for theta hat would be like this. So here we assume that although b is unknown, but the sign of b is known. Okay, if you extend this to the vector case, the sign of the matrix B is a little hard to think about. You could probably think about knowing the signs of the different entries of the B matrix, but that would be a little unreasonable to assume. So the case where both the A and the B matrices are unknown is a little hard, but you can try that on your own. There are some assumptions that you have to make, and the result may not be global, although you may end up with a global result. If you come up with a result like that, you could probably publish a paper in a good journal. Okay, so so with this we are able to cancel all these terms, and we end up with v dot equal to a m e square. So which means that the equilibrium point, so this is negative semi definite. Okay, so the equilibrium point given by E equal to 0, k x tilde equal to 0, k r tilde equal to 0. The origin is Lyapunov is stable, Lyapunov stable. Okay, and since v is greater than 0 and v dot is less than equal to 0, we can similarly say that v is bounded, which means that E of t k. So this signal chasing is something that you all should do, although it looks very similar to what we had done before. It is important that you go go through with it. In the indirect case, we found that when we go through with it, the control input is in fact not bounded in a certain case, and so we have to modify our update law. So it's important that you prove that all signals are bounded. Okay, so using this we can further show that x of t, kx hat of t, kr hat of t, and theta hat of t are bounded. Okay, so what is left is to prove that the control input u is bounded. So if we go back to the controller, we see that we have proved that kx hat is bounded, proved that x is bounded, kr hat is bounded, r is given to be bounded, theta hat we just proved to be bounded from the Lyapunov analysis, and phi. So we have to assume here that phi is bounded whenever x is bounded. So that's an extra assumption that we make on the basis function. The basis function here is such that the assumption here for the basis function is that phi of x is bounded if x is bounded. So we have already proved using this analysis that x is bounded. So we can say that the basis function phi is also bounded, and so we can say that the control input u of t is bounded, right. And then similar to the previous case, we can also go ahead and use the Bartlett's lemma. So we can easily show, like previously, that E of t and E dot of t are bounded, and the fact that E of t is L2, and then Bartlett's lemma could be used to show that E of t goes to 0 as t goes to infinity. So again, in this case we have been able to prove that the tracking error converges to 0, although the same cannot be said about the parameter estimation errors. All we can say about the parameter estimation errors are that they are bounded. In many cases, this is all we need. Our most important objective is for the tracking error to go to 0. Okay. So that is all about the case where you have a matched structured uncertainty like this. We have done the scalar case. You can also attempt the vector case for this. It is very similar to this analysis. Okay, and this is in fact a realistic scenario because real systems are not entirely linear. There is always some nonlinearity or the other, and if we can say that nonlinearity is linearly parameterizable, then we can use this kind of a model reference adaptive controller to stabilize the overall system. Okay, so now I move on to a slightly different problem, which is the command tracking problem. So far what we have discussed is a model reference adaptive control approach, where there is a plant which is any system that you are considering, for example, an aircraft or a chemical system or a biological system, which is linear time invariant system, or the case that we just did with structured uncertainty. And then there is a reference model which we want the plant to follow. So the objective is given in terms of a reference model which encapsulates the desired behavior that we require from the plant. Sometimes the objective can simply be a tracking objective, that is, we want the plant state to track some desired time varying signal. So that is the problem of adaptive command tracking, which we will do now. Adaptive command tracking. So, again I consider the scalar case, but you could again go ahead and do the vector case. It will be slightly more involved, it will involve traces in the Lyapunov function, but the approach is similar. And why I am using this this case is because it's easier to follow, and for students who are interested in learning more about it, they can go ahead and do the more complicated vector case. Okay. So, again the plant is a linear time invariant plant given by A x plus B u. We say that B is non-zero for controllability, and the object. So, there is no reference model here. So, we do not want x of t to follow some state of a reference model. Instead, the objective is given in terms of a desired trajectory, which is x d of t. So, we want x of t to follow x d of t. So, x d of t could be any time varying signal of your liking that you want the plant to follow, and what we assume here is that this desired trajectory is smooth, it can be differentiated, and these derivatives are bounded. So, we say that x d of t, so up to the second derivative we say that it is bounded. So, we will see where this assumption is used. Okay. So, whenever we we are given a problem like this, we always start with the tracking error. E of t is defined as x of t minus x d of t, and then we try to find the error dynamics. So, the open loop error system is given by taking the time derivative of the tracking error, which gives A x plus B u minus x t dot. Okay. Okay. So, just for my ease of analysis, what I do here is I add and subtract the term A x d. Okay. So, what it does is it converts the error system into a form which is similar to what we had obtained before. So, it just helps to make the analysis easier. So, but does not change anything mathematically. So, E dot is A e plus B u plus A x d minus x d dot. Okay. Now, assuming that A and B are exactly known, how would you design the controller U? So, suppose A, so I make the assumption that A and B are known. So, then we could design the controller U as 1 over B. So, we want to cancel terms that are unwanted here. So, we since A, although A is known, it can be either positive or negative. So, we want to cancel this term, and we want to place our own term A m here, and we also want to cancel these two terms, because they are not really helpful in proving that E goes to 0. So, we want to cancel these term involving the desired trajectory. So, we would use minus A over B x d plus 1 over b x d dot. So, if we use this and substitute this in our open loop error system expression, then we would get E dot is equal to AME, where AM we have chosen to be less than 0. So, AM it could be any desired value, but you could also think of it as as a pole, that as a desired pole location that you want the system to obtain. So, the closed loop error system in this case would come out to be E dot equals AME, and AM would then represent the desired pole location. So, this could also be thought of as a pole placement controller, adaptive pole placement controller, where the idea is that instead of the open loop pole location, we want to place the pole at some desired location given by AM, which is on the left hand plane, and this controller would do the job. But here we assume that both A and B are exactly known. So, what if A and B are not exactly known? So, like in the previous case, we just simply use a certainty equivalence controller. So, for the case where A, B are unknown, which is the adaptive case, the controller U is simply given by taking the estimates of these unknown terms. So, we have minus A hat plus A m. So, wherever you have these terms, we replace them by their estimates. Okay. And we can call these coefficients as K1, K2 and K3. In fact, K1 hat, K2 hat and K3 hat, and these could be K1, K2 and K3. Okay. So, since we do not exactly know A and B, we also have K1 hat, K2 hat and K3 hat. But what we do assume is that there exists K1, K2 and K3 such that the matching conditions again come into play. So, they can be directly found from the algebraic equation expressions that we had formed. So, BK1 is equal to minus A plus AM, BK2, let us look at what it would be. So, this entire expression is equal to K1. So, BK1 is minus A plus AM, A over minus A over B is equal to K2. So, BK2 is equal to minus A, and 1 over B is equal to K3. So, BK3 is equal to 1. So, these are our matching conditions for this case. Okay, so, U is given by K1 hat E plus K2 hat x d plus K3 hat x d dot. So, here K1 hat, K2 hat, K3 hat are the estimates of K1, K2 and K3. Okay. So, let us now substitute this into the open loop error system and get the closed loop error system. So, the closed loop error system is given by E dot AE plus B. So, yes, A plus B K1 hat E plus B K2 hat plus A x d plus B k3 hat minus 1 x d dot. Okay. So, so here we use the matching conditions and replace the terms which are unknown, that is A and B, but we should be a little smart about the substitution. So, here because we want to combine B k1 hat with this term, we choose the matching condition given by this to replace A by AM minus BK1. So, this is AM minus BK1, this is obtained from the matching condition 1. The second term in the bracket BK2 hat plus A, we can manipulate this by replacing A in this case by minus BK2, which is given by the second matching condition. So, here we replace this by minus BK2, and now because we want to combine BK3 hat with the matching term so that we get an error, we replace 1 here by BK3. Okay. So, after making these manipulations, what we get is AM E minus B k1 tilde E minus B k2 tilde xd minus B k3 tilde xd dot. All right. So, this is our closed loop error system for the command tracking case. Okay. So, now the next step would be to again consider Lyapunov function candidate and try and prove stability. So, the Lyapunov analysis will also help us in designing the update laws for k1 hat, k2 hat and k3 hat. Okay, so, let us choose the Lyapunov function. So, we want to choose a Lyapunov function which involves these error states, the tracking error and all the parameter estimation errors k1 tilde, k2 tilde and k3 tilde, and we want that the entire function should be a scalar, should be positive definite. So, these are some of the things that we have to keep in mind. The first thing that we always try is a quadratic function. It just makes it simpler, but there could be many choices available which could yield similar result. Okay, so let us choose the Lyapunov function as, so because it is a scalar case, it becomes easier for me to choose it very similar to the direct MRAC case. So, gamma 1, gamma 2 are positive quantities which we will see would be the adaptation gains. Okay. Okay, so let us now take the time derivative and substitute for the error dynamics. So, V dot is given by E dot plus Okay. So, now I have set up the problem for the development of the update laws. Okay. So, let us substitute for the closed loop error system. Minus b over gamma 2 k2 tilde k2 hat dot minus b over gamma 3 k3 tilde k3 hat dot. Okay. Okay, so now let us choose the update laws for k1 hat, k2 hat, and k3 hat. Okay, so k1 hat we want to choose so as to cancel this term involving b k1 tilde e. So, the way to choose this would be to use a minus gamma 1 e square and sine of b. Then we want to choose k2 hat dot in such a way that we could cancel this term. Again, why we are cancelling this term is because these are not really important, not really needed in the Lyapunov derivative. We want to have terms which are sign determinate and preferably negative, so that we can take care of them. So, these terms which we want to cancel are their signs are not really known, because they are dependent on these error states and the desired trajectories, which vary with time, and their signs also may vary. So, so k2 hat dot is designed like this, and so E x t signum of b. Okay, and k3 hat dot we will design similarly to cancel the last term in the brackets. So, which will be E x d dot signum of b. Okay. So, if we choose these update laws, so these are the adaptive update laws. Okay, one more thing to notice here is that so since we have used k1 hat, k2 hat, k3 hat, and we have gone ahead with the analysis with these estimates. This is a direct approach. We can also do an indirect approach where we simply consider a hat, b hat, and go ahead with the analysis, and then try and design the update laws for a hat dot and b hat dot. So, that is something that you could try on your own. This is the direct adaptive command tracking controller. Okay, so substituting these in v dot, what we get is v dot is am times v square. Okay, so again this is negative semi definite, and you could say that the equilibrium point is Lyapunov stable. It's important to go through with the analysis, and we can show that V is bounded, which implies that E of t, k1 tilde of t, k2 tilde of t and k3 tilde of t are all bounded, which further implies that x of t is bounded, because we have assumed that x d of t is bounded, and since k1 is simply a constant, so k1 hat of t is also bounded, k2 hat of t and k3 hat of t are all bounded. Okay, and then we can go back and try and prove that the controller is bounded. Okay, so here we see that k1 hat is bounded, E is bounded, k2 hat is bounded, xt is bounded, k3 hat is bounded and xt dot is bounded, because that is something that we had assumed. So, since all these terms are bounded, what we can say is that the controller u of t is also bounded. Okay. So, what we have not shown here so far is that the tracking error E of t goes to 0. So, let us go ahead and prove that. So, we already proved that E of t is bounded, and using similar to previous analysis, we could also prove that E of t is L2. So, that is apparent. The thing we have to be careful about is proving that E is uniformly continuous. So, for that we need to look at E dot and prove that E dot is bounded. So, let us look at E dot. So, E is bounded, k1 tilde is bounded, E is bounded, tilde is bounded, xt is bounded, k3 dot tilde is bounded, xt dot is bounded. So, all these terms are also bounded. So, what we can say is that E dot of t is bounded, which implies that E of t is uniformly continuous. Okay, and using these three facts, we can claim using Barbalet's lemma that E of t goes to 0 as t goes to infinity. So, okay. Okay, so in this lecture, what we have, you can in fact go ahead and do the indirect adaptive tracking controller. Okay, so in this lecture we have studied two different controllers from what we had done before. The first one is a case where we have matched structured uncertainty. The fact that the uncertainty is linearly parameterizable allows us to use the adaptive control approach and design the entire controller as an adaptive controller. So, there we have a nominal controller, which is the MRAC controller, and a controller which is used to account for the nonlinear term, which is again an adaptive controller. For cases where we have unstructured uncertainties or uncertainties which are not linearly parameterizable, it is not straightforward to use adaptive controllers. They are popularly used for cases where the uncertainties are linearly parameterizable. The second case that we discussed today was a related case where instead of the plant following a reference model, the plant state tracks a desired time varying signal given by which we assume to be smooth, with bounded derivatives. So, using a direct adaptive control approach, we designed we designed a stabilizing controller for this case, and you can go ahead and do the indirect command tracking adaptive controller. Okay, so in the next lecture, in fact in the next few lectures, what we will discuss is robust adaptive control, where instead of the uncertainty being structured uncertainty, the uncertainty is unstructured, and how do we tackle that case. So, normally we use some kind of a robustifying elements in our control laws, either the controller or the adaptive laws, which make sure that the stability is preserved. So, in the next couple of lectures, we will study robust adaptive controllers. Thank you.